Australia. We're very happy to have her here. I should say that she is also rejoining, she's joining ANIT as a collaborating member of Joao's chair on lever on explainability. And so we're very excited that she's here. She's a expert, world expert in planning, and also runs the Journal of Artificial Intelligence. And so she's an important person to know for all of you. And we're very happy again that you're here. Sylvie, you have the floor.
Thanks very much, Nicolas, and thanks for inviting me. I get an echo, so maybe you want to mute yourself. Okay, perfect.
Everybody, can you turn off your mics so that Alexandre, par exemple, voilà.
All right, so it's really good to see some familiar names over the internet and also some new ones. I'm Miss France, and I'm hoping to see you in person very soon. All right, so for this talk, given the focus of on NET, oh, sorry, there's another echo here.
Jayan, tu peux fermer ton micro là, merci.
Yeah. So given the focus of NET on hybrid AI, I thought I would talk about deep learning for planning. And so that's joint work with my colleagues, Florian Geisser, Felipe Trevisan, Lexin Xie, and with two pretty amazing undergraduate students. We had the opportunity to supervise at ANU. They've now graduated, they moved on, and they're doing their PhDs at MIT and Berkeley, respectively. So before I can even state the kind of questions that we were trying to answer, I thought I would give everybody a little planning refresher, because otherwise I think if you're not familiar with planning, it's going to be pretty difficult to understand the talk. And so if you are familiar with planning, just go and have a coffee and yeah, come back in 5-10 minutes. So in planning, what we're trying to do, the basic problem is to generate a course of action enabling an agent to reach given goals in its environment, starting from an initial state. So for instance, for this household robot here, we might give him the goal of having all of the rooms clean, or perhaps to serve breakfast in the living room. Now, from a computational point of view, planning amounts to finding a path from an initial state to a goal in a gigantic transition system whose states represent the states of the environment and whose transitions are labeled by the actions that the agent can take. Now, if the actions are deterministic, if there's no uncertainty, then we can simply take a plan to be an action sequence, which is going to basically create a path from the initial state to the goal. And we usually try to optimize the cost of the plan for some notion of cost. If, on the other hand, there is uncertainty, for instance, if you can't fully predict the states resulting from applying an action, and so the actions may appear as deterministic or stochastic, then we're going to generate policies. A policy is a function that maps the current state to the action that the agent should execute. And so when we execute a policy, we start at the initial state, we execute the action that the policy prescribes for this state, the environment then change states, and then we get a new state from which we execute the next action and so on until we reach the goal. So you may wonder, well, if planning is just path-finding or stochastic path-finding problem, why is it so hard? Well, it's hard because the transition system is huge. I mean, even in this little toy example, if you have X rooms and Y objects, which the agent can move from room to room, you'd have X to the Y states. And so you can imagine what happens for a real world problem, which may have resources, time, etc. You end up in a case where you basically cannot even give the transition system explicitly. And so for that reason, the planning community over many, many years has developed compact representation of these huge transition systems, which enable algorithms to very efficiently explore this state space. So the representation I'm going to use in this talk is the most basic one, strips. It underlies many of the modeling languages used for planning, like PDDL, which you may have heard of. So in PDDL, we're basically going to split the description of the transition system into two parts. So even if you know planning here, I would like you to listen, because just to pick up the vocabulary I'm going to use, I think that's going to be useful. So the first part is the domain, and this lists the predicates that represent the relationship between the objects in the environment. For instance, that there is a path between two locations, or the properties of the objects in the environment, if you like. And it also lists the action schemas that represent the type of actions that can be taken. So for instance, that a robot can drive between two locations. And that's characterized by preconditions that must be true for this type of action to be applicable, and by effects, which basically describe the changes that the action is going to make to these predicates. And you can have probabilistic effects, like this one only has 90% chance happening, and you can have cost of actions and so on. So that's the domain. And then the second part is the problem. In the problem, you're going to list the objects that are in the particular configuration you have. So basically, a problem is an instance of the domain. So you list the object. For instance, we have a robot in 3 rooms. You list the propositions that are true in the initial state, and these are instances of the predicates. For instance, at shaky kitchen is an instance of this predicate obtained by grounding the predicate, substituting its parameters with some of the objects in domain. And you have the goal proposition that must be true in the goal state. Similarly, what we're going to call actions are instances of the action schemas obtained by grounding these action schemas, like drive, shaky, kitchen hall is an action. So this is basically the bare bones of PDDL. PDDL additionally can represent many other things like time, resources, uncertainty, hierarchical decomposition, and so on. So all of the ingredients that makes it possible for planners to solve real-world problems. Now, I should warn that in this talk, I'm not going to talk about real-world problems. I actually do very much enjoy solving real-world problems, but it's just not going to be that kind of talk. All right, so what's a planner now? Well, a planner is a general purpose solver that takes as inputs the description of the main problem and return a plan or a policy solving the problem. Planning is pretty complex. So even once you've grounded all of the predicates and the action schema to obtain the proposition and action and take this as input, it's still p-space complete, the most basic kind of strips that I've shown you. And if you start adding things like numerical variables to represent resources and so on, then it can become even undecidable pretty quickly. So what are the main methods that are used in planning? There's a whole range, but there are 2 things that stand out. The first one is to convert the problem into a series of constraint satisfaction or constraint optimization problems that can then be solved with high performance solver like, I don't know, SAT, SMT, MIP, I mean, you name it. And the second most important technique being used at the moment is search, and in particular heuristic search. So things like greedy best first search, A*, or if you have uncertainty, LRTDP, variants of Monte Carlo tree search, and so on. So the last thing I want to say to end this intro to planning, I want to talk a little bit about heuristics because they're going to be important in the talk. So in search and planning, a heuristic is not some sort of dirty trick or a rule of thumb. It is a precise meaning. And it's basically a cost estimator, which is going to be used to guide the search of heuristic search algorithms like A*, for instance. So a heuristic is a function that takes as input the current state and returns an estimate of the cost of reaching the goal from that state. You may have heard of admissible heuristics. What they are heuristics that always underestimate the optimal cost of reaching the goal. So H of S is always an underestimate, and that's important because that guarantees that algorithms such as A* will find cost optimal solution if you've got an admissible heuristic. So you could think, well, if every time I want to solve a new problem or even some problems in a new domain, I have to come up with dedicated heuristics, then really these heuristic search planners aren't general purpose solvers after all. Well, fortunately, the planning community over the past 2 decades has come up with a wide range of domain-independent heuristics. So there are heuristics that can be automatically computed from the domain description. And the main approach to compute them is to relax that domain description. So we simplify it, we remove some constraints, some elements of it, until we get a problem that's simple enough to be solvable in low-order polynomial time. And the cost of the solution to that relaxed problem is a heuristic. And furthermore, the cost of the optimal solution to that relaxed problem is an admissible heuristic. So this is how we generate our heuristics to guide search. And I'll just give you one very simple example of a relaxation. It's called the delete relaxation. What you do is that you remove all the negative effects of action. So you remove the fact that this robot is not in the previous room that it was in. When you remove all negative effects, this is solvable in a polynomial time because every time you apply an action, new proposition gets achieved and they never get deleted because you don't have negative effects. So eventually the goal proposition will be reached if the problem, the delete relax problem is solvable. And any action only needs to occur at most once. This delete relaxation is not solvable optimally in polynomial time, but you can do further relaxations that will ensure that it is. And in fact, some of the very popular delete relaxation heuristics, such as those that I'm going to mention, like Hmax and LMCut, which are admissible, do this. And I also, in the talk, refer to other heuristics that are inadmissible, like FF and HI. All right. So now let's go back to deep learning for planning. So the main question we wanted to address in this, or start addressing in this research, is to figure out whether deep learning can learn to solve planning problems. So we know that deep learning is now the method of choice for perception tasks like in computer vision or natural language processing, but it's still unclear the extent to which it can be helpful to learn to solve reasoning problems such as planning. And so that's the broad question, basically, we were interested in. And so as a starting point, what we thought is that rather than reusing off-the-shelf neural network architectures like convolutional neural network or recurrent networks, we would instead design a new architecture which exploit the structure of planning problems, would exploit the type of representation that I've shown you in order to more efficiently learn. So our conjecture was that if we do that, we exploit structure in terms of precondition, effect, action schema, predicates, then we're gonna require much less time and training data to learn. Now, instead of learning to solve specific problems characterized by specific initial states, specific goal, and a given set of objects, we thought that we would rather use deep learning to learn to plan in a domain. So basically, generate policies that are general enough to be applicable to all problems for a domain. Remember the difference between problem and domain. And similarly, we thought that we would learn heuristics that are applicable to many problems in the domain and even maybe across domains so that we can for instance, learn a heuristic on blocks world and use it on a more complex problem. So these questions, I think, are non-trivial, and people on both sides of the fence, the learning and planning side, would agree to this. So if you have a look at the talk of Yann Lequin, that's his keynote talk at AAAI 2020, he gave learning to plan complex action sequences as one of the top 3 challenges for deep learning. And he also added that he wasn't going to talk about this in his talk because he had no idea how to do this. Another top 3 challenge, according to Yann, is learning with fewer labeled samples and of fewer trials. And he said that a good way to start on this would be actually to learn to represent the world before we start learning tasks. And so you can see that this is perfectly in line with what we're trying to do here. Now, if we look on the planning side, Hector Geffner, prominent planning figure at his ICAPS 2018 talk, said that AlphaZero is impressive because it's learned to solve fixed size board games, such as chess or Go. But it's not capable of solving arbitrary instances of simple planning benchmarks, such as blocks world, even though it's simpler. And so he basically offered the challenge to the community of doing that, of coming up with a general learning algorithm that can learn to solve arbitrary blocks world problem, regardless of their size, initial state, and goal, which is exactly what, as you will see later, our generalized policies are enabling us to do. So our contribution and what I'm going to present in this talk is basically 2 different architectures that exploit the structure of planning representations to learn more efficiently. So the first one is called action schema networks, and it learns policies that generalize to potentially all problems for a given domain. And the second one is TRIPS hypergraph networks that learns heuristics that generalize not only across problems within a domain, but also would try to set up the learning problem in such a way that they potentially generalize across domain, very much like one of the domain-independent heuristics that I've talked about in planning do. And so you can see maybe action schema networks as the equivalent to planning of what convolutional neural nets are for image processing, whereas this architecture here is more a graph network architecture. So I'll talk about them, about their properties and how they work, and I'll give you some experimental results. And to conclude, if I have time, I'll talk a bit about how this fits in my broader agenda of research of building trustworthy systems that combine planning and learning. All right, if everybody's, yeah. Okay, so let's start with AISNets. So this is an AISNet, and what it represents is a policy. So that takes as input features of the problem we're trying to solve, particular features of the current state and the goal trying to reach, and outputs either an action or a probability distribution of our actions to be taken in this current state. So I'll detail a little bit more what's in the input and the outputs in a minute, but for the moment, I want to concentrate on the structure of the network. So as you can see, AISNets consist of alternating layers of actions and proposition modules, with the first and last layer being an action layer. Each action layer has one module per action in the problem. So that's going to grow with the number of actions, grounded actions. And similarly, each proposition layer has got one proposition module per proposition in the problem. Now, we only have connection between adjacent modules that represent related proposition and actions. So The relatedness definition is as follows. Say that an action A and proposition P are related if and only if P appears in the preconditions or effects of the action. And so thanks to this relatedness relation, we're going to be able to very efficiently propagate information through this network for the purpose of deciding the action to apply in the current state using the structure of the planning problem. Because if you're trying to, well, there's basically no influence unless you are on a chain of related proposition and action. There's basically nothing that's going to influence the choice of the action. So we're really going to be able to exploit the structure of the problem. Just to zoom in a little bit, what's in these boxes? This is an action module for the action drive, shaky kitchen, all. And you can see that it's related to 3 propositions at the previous layer, which represent its preconditions and effects.
Il y a encore une conférence où j'étais invitée. Et quand je comprends.
Someone has got their their mic on. All right, we're good. All right. So what was I going to say? Yes. So it takes as input vectors coming out of these modules. First thing that it does, it concatenates those feature vectors. And then it applies, as is usual in neural network, a linear transformation, multiplying by a matrix of weights, adding a bias vector, and then applying a nonlinear transformation like a rule or something to compute the outputs. So what we're trying to learn are these matrices and this vector, and we're going to learn it using examples of policies or plans. Very importantly, the dimension of these matrices here can be set once and for all, so that in such a way that the dimension of all the input and output vectors in all the network are the same. So similarly, we have proposition modules. They're a little bit more complicated. So that's proposition module for the proposition add shaky kitchen. It's got 2 related action modules, which have add shaky kitchen in their precondition or effect. And the first thing that we do is that we pull from the vectors coming from these action modules that share the same action schemas. So you can see these 2 actions, they have the action schema drive. We're going to pull them together, I don't know, taking the average, sum, or whatever. And so that, for instance, if you had another action, other action schema like go, which does the same as drive but more slowly, we would also have 2 related go action here, and we would separately pull from them because they're from a different schema. So at the end of the pooling, we have at most 1 pull vector per action schema. We again concatenate them and apply the linear and nonlinear transformation. And you will see why we're doing this pooling in a couple of slides. All right, so the input features to the actions of the first layer are very simple. We give the action as input a Boolean saying whether it's applicable in the current state. And we can determine that from its precondition easily. And then for all propositions that are related to the action, we give the module the value of that proposition in the current state and in the goal. So no uncrafted features, very simple. And finally, the output. We transform the logits out, which are the output of the last layer, into a probability distribution over actions by passing it through a masked softmax layer. So these masks here are going to be Booleans saying whether the action is applicable or not. So as a result, all actions that are not applicable, they have a 0 here, will have a probability of 0 of being applied. All right, so at this point, you might be wondering, well, you might be thinking, well, come on, you've told me that these policies were going to generalize to all problems in a domain, but how can we do that when problems can have completely different number of objects, configuration, and when the network actually, the way it looks, completely depend on the number of propositions and actions, which itself depends on the number of objects. So we're going to get completely different networks for different problems. So how can we transfer our knowledge between these? Well, the key to figure out how to do this is to realize that whilst the number of proposition and action does change, there's one thing that does not change if the problems are all from the same domain. It's the set of predicates and action schema. That's the same across all problems. So in order to be able to transfer knowledge between problems, what we're going to do is we're going to share weights, these weights we learn across modules, which are made from the same predicate or the same action schema. So specifically within a layer, all proposition modules built from the same predicate are going to have the same weights, and all action modules built from the same action schemas are going to have the same weight. So that here, for instance, if we have another drive action at the same layer, drive Bob from the toilet to the ballroom, then this matrix here and this vector will be the same for these modules. And that's okay because they have the same number of related propositions, because the action schema has got an exact number of them. And these even play the same role from the point of view of the action. For a proposition module, it's a bit more complicated again. This is a proposition, add shaky kitchen. If we had another proposition module like add Bob, I don't know, hole, it would also have the same weights as this one. However, for propositions, a little bit more tricky because when you increase the size of the domain, you can have more related actions. For instance, if we had a ballroom, we would have drive shaky kitchen ballroom and drive shaky ballroom kitchen, also related to this add shaky kitchen. So we don't have the same number of vectors here, but because we pull from the vectors sharing the same action schema, at the end, we're still going to have one pull vector per action schema. So it's not, after the pooling, we're not going to be dependent on the size of the problem. And this is why the weight sharing works. All right, so before I present experimental results, I just want to mention one of the main limitations of AISNets, and that's their limited receptive field. So this is analogous to what's happening with convolutional neural networks. So the receptive field of a unit in a CNN is, let's say, the window of pixels that determine the output, that influence the output of this unit. And so in the lower layers of the network, it's a very small window. And as you aggregate and propagate information upwards, it's going to be a bigger window. But if you don't have a lot of layers, maybe it's not going to be the whole picture. So it's the same here for an AISNet. The receptive field of a module is the set of input propositions that are going to have an influence on its output. And again, for the bottom layer actions, it's just the direct inputs. So it's a small set. And as you aggregate and propagate information according to the relatedness relation, then this set is going to grow. But because AISNets have a fixed depth, they can't reason about arbitrarily long chains of related proposition and actions. And so what can happen is that you're here at the last layer, you're trying to determine the probability with which this action should be applied. And there is input information you don't have access to by one of these chains, something here, for instance. And if this is crucial information, like, you know, what some of the goal propositions, you don't know what goal you're trying to achieve, it's going to be very difficult to get a good policy. So to remedy this, we're going to give additional inputs to these first layer modules. And in order to do that, we're going to use information computed by domain-independent heuristics, such as those we have in planning. We're going to use information computed by LMCOT, which is one of the admissible heuristics. As part of its computation, LMCOT computes what we call disjunctive action landmarks. Such a landmark is a set of actions, at least one of which must be executed in order to solve the problem. So it will be executed in any plan for the problem. So what we do is that we give the input layers here a 3-valued number saying whether the action is in a LMCOT landmark, whether it's in the singleton LMCOT landmark, in which case we know it's going to have to be applied, or whether it's not in a landmark at all. And so the corresponding action at the last layer will have access to the information because it's related to itself via its preconditions and effects. And so that gives a lot more information to the network whilst remaining domain independent. So I'm going to show you some results on planning benchmarks. Before that, let me say that the way we learn the weights of these networks is using an imitation learning approach that learns the weights in such a way as to mimic the decision that a teacher planner would take on a set of small planning problems. So for blocks world, we're going to train on small planning problems between 8 and 10 blocks, and then we're going to evaluate the policy on much bigger problems. I also want to mention that you'll see that we're using very few computational resources here, just one core. That's in order to be fair with the planners that are not parallel. We don't use, gigabytes of memory. And we also have very shallow networks. So it's hardly deep learning, 2 to 3 proposition layers in addition to the extreme ones. But these networks still, because they're very wide, they can still have tens of thousand nodes, like for a 50 blocks problem, for instance. So blocks world, okay, it is a very artificial benchmark, but it's actually quite hard. It's NP complete to solve optimally. And 50 blocks is very challenging for a general purpose planner. So blocks world consists in transforming a configuration of block into another by moving blocks that are on top of a tower to another or onto the table. It's a very simple problem, but hard. So what I'm going to show you is graphs of this type, where in the x-axis you have the time that we're going to take to solve these 30 evaluation problems altogether. And here's basically how many problems we solve. So that's the coverage. So you can see in blue here, we've got ASNets. It solves nothing for an hour because it's training, and then it's going to solve all of the problems pretty easily. In orange here, you have ASNets without heuristic inputs. And so you can see it learns for longer and it cannot solve some of the problems. And that's because in blocks world, you can have high towers. And due to the limited receptive fields, if you're trying to decide whether to stack something on top of this tower, you may not have, via related proposition action, access to the information of whether the bottom block in the tower is already in it, or the 2 bottom blocks are in their good position. So you don't know whether you can make sense to apply the action. This is why we don't solve all the problems. Now, the planners that I'm gonna compare with, there's 3 of them. The first one is in green, it's Llama first. So it's a very fast planner, which returns very low quality plan. And in fact, the plans that ASNets return are much higher quality. You can see it doesn't need to learn, of course. It solves all the 35 blocks problems and then cannot solve the 50 blocks one, even though it's super fast. The other extreme here in red is A star. So this is very high optimal quality plans, but A star cannot solve any of those problems with an admissible heuristic. And in purple here, I've represented greedy-based first search with the LM-cut heuristic, just to show you that it's not because you have LM-cut that you have this heuristic information you can solve the problem. So we are learning something here. And what's more, the policy that we get, we also evaluated it on 20,000 random problems and found that we could solve all of them except 3. So I think we can claims with some caveat to have solved Hector's challenge. I'm going to show you another domain, which is a probabilistic domain called triangle tile world. As you can see, we saw, so the problem is basically to reach a goal state in a network of nodes and roads, where every time you move to the next location, you have a non-zero probability to have a flat tire. And the black locations have spare tires. So the only way you can actually reach the goal with 100% probability is to take the outer edge through the triangle. So we train on 3 problems. So you can see it's hardly, you know, AlphaGo, and it's, you know, I don't know, centuries of training time and petabytes of data. 3 training problems. The largest one is actually this one. And then we evaluate on larger problems. And again, on these probabilistic problems, IceNets, even without heuristic inputs in this case, manage to solve all of the problems, whereas the heuristic search planners here are struggling. So one nice little thing with this policy is that when we inspected the policy to see what it was doing, it had a very nice characterization of the best, basically the policy to use. And it basically said, well, at each step, move to a location from which 2 spare tires are accessible in a row. And it's, even though I designed these problems with a student way back, it never came to my mind that to think of the policy in those terms. So it's kind of interesting that, yeah, the network can learn it. And finally, this is a much more complex problem called exploding blocks world. What happens is that some of the blocks can explode, and when they do, they destroy other block, which may make the goal unreachable. And in fact, in some problems, definitely the goal is not reachable with 100% probability. So in fact, here we measure, you know, the expected number of time we reach the goal over all of the problems, and we don't even know what is the number we can reach. Definitely not 30. So with this problem, you have to learn. We learn actually with an admissible. We learn from optimal plans, because yeah, it's very tricky. You need to be very careful at each action. And with that, we managed to, you know, solve more problems than probabilistic planner in gray here, but the results are disappointing. And so that shows that when the problem becomes really complex, we're going to need to combine learning with reasoning. There are problems we can't solve. So at the moment, at least with the small computational resources we have, Sokoban, people who have come up with a policy that generalize a little bit for Sokoban, like Peter Abil and its students, have used 3 order magnitude more data and time. And it's also a dedicated approach kind of to Sokoban, so it doesn't solve all the problems. The 8 puzzle, we can solve all the 8 puzzle problems with our policy, but doesn't generalize to 15 puzzles. And maybe that's due to the, you know, choice of, we use training problems from the planning competition, so they are not really building a very good curriculum to learn. All right, so my takeaway on IceNets is that so it's the first deep learning approach to generalized planning. It exploits the structure of planning in terms of the precondition effect relationship, and thanks to that, you can learn with a small amount of training data. It has a weight sharing scheme, which enables it to generalize to problems from different domains. And that generalizes quite well, at least when there is a simple local trick that you can learn from small problems, like the local trick in triangle tile world of moving towards 2 locations that have got a spare. So this work well when there is these local tricks, but for more complicated problems, we're really gonna need to combine learning and search if we want to solve them. And that leads me to the second architecture, which is TRIPS-AGN. So what we're trying to do here is to learn heuristics to guide the search. So remember, heuristics estimates the expected cost to reach the goal from the current state. So what we wanted to do is to learn heuristics entirely from scratch by training on optimal plans for a set of TRIPS problems. There has been actually approaches to learn heuristics in the past, even using deep learning, but that was before the deep learning revolution. And these approaches used handcrafted features for the problem. They also tend to improve on an existing heuristic rather than generating a new heuristic entirely from scratch. So our hope was that we would manage to learn heuristics that generalize to problems from different domains, so problems with different initial state goals and number of objects. But we're also hoping to find an approach that would learn heuristics that can generalize across domains, so that, for instance, maybe we can learn a heuristic for blocks world and use it to guide search for exploding blocks world, for instance. So that is really, we're basically trying to learn domain-independent heuristics, the kind of domain-independent heuristics that we have in planning. All right, so in this part, I'm going to assume that the domain has already been completely grounded, so we have just proposition and actions. We're not going to bother with the action schemas and the predicates. So TRIPS-AGN also exploit the structure of planning problems, or these grounding planning problems, and in particular, it exploits the structure of the delete relaxation heuristics that I've talked about. So remember, the delete relaxation heuristic, or the delete relaxation of planning problem P is P plus, which ignores completely all of the negative effects of action. So we removed all negative effects of action. That gives us a relaxed problem. We call it P plus. And that delete relax problem can be represented by a hypergraph. So the nodes of this hypergraph represent the propositions in the problem. And the hyperedges of the hypergraph represents the actions. And these hyperedges link the precondition of the actions to the positive effects. We're going to call the precondition, or this part of the link, the senders, and this one the receivers. So this is just one hyperedge. You can imagine if we had all of the propositions and all the actions, so we'll have hyperedges everywhere, and that will be the hypergraph. And so what we want to do is to learn a cost function or a distance function, if you like, over this hypergraph. We want to learn to predict some sort of notion of shortest path in this hypergraph, which is going to reflect our training set. And that training set consists of pairs, a state of the environment, and the optimal cost of reaching the goal from that state. So we're learning from the perfect heuristic. If we add that, then the problem would be solved. Okay. So concretely, we're going to learn function H that takes as input the hypergraph representing the delete relax problem, and is going to return a real number representing the heuristic value. Of course, the hypergraph is going to be augmented with features, and because we want to learn from scratch, the input features are going to be basic. For each of the vertices of the hyperedges, we're going to use as features the costs, precondition, and the effects of the corresponding action. And for the vertices, we're gonna use the truth value, true or false, of the corresponding proposition in the current state and in the goal. So you can't come up with more, simpler features. May as well not have them. All right, so how do we learn this function? Well, we're using hypergraph networks. That's our own extension of, a very slight extension of graph networks by Peter Battaglia and other people from DeepMind. And I don't know whether you've read the graph network paper, but it's very nice. It extends many learning models and not just deep learning. So with hypergraph networks, basically the building block of the network is going to be a hypergraph network block, which I've represented here. What this does is that this transforms a hypergraph described by hyperedges, features, vertices, features, and global features into an updated set of features. So an hypergraph with an updated set of features. The global features, we're going to use them to represent the value of the heuristic function. So how does this work? Well, this transformation is made using 3 update functions in green here, and they're learnable. This is what we're going to learn. And in our case, we're going to represent them as linear perceptrons or multi-layer linear perceptrons. We also have 3 aggregation functions in red here that are going to basically aggregate information from various parts of the hypergraph and propagate the information through the hypergraph using essentially a message passing. And so for that, we're using things like sum, nothing fancy. So basically in one round of message passing through this block, the following is going to happen. Firstly, we're going to call the update function to update all of the features of all hyperedges using their current features, the features of the vertices that they're connected to, right? So that exploit the structure of the planning domain, and the global features. And that's going to give us updated hyperedge features. Then we're going to update all of the features of the vertices by aggregating considering their current features and also the aggregated updated features of the edges for which these vertices is a receiver. So again, we're only propagating information between bits of the hypergraph that are connected. And then we're going to update the global features using all aggregated information from the graph. So that's one round of message passing. And our overall architecture is just 3 of these hypergraph network blocks. One that simply encodes the hypergraph into latent space. Another one that decodes the latent representation of the heuristic into a value. And then this core block that does the message passing. The core block actually is used in a recurrent way. So at each step, it concatenates the latest hidden latent representation with the latent representation of the original graph. That's just to make sure we keep track of where we are in our message passing and learn. And even though we're doing M round of message passing before stopping, in fact, we can decode a heuristic at any point after any number of message passing round. So how do we train this? Well, we generate optimal plans for a number of small planning problems. And so that when we have a plan, we can have a look at the intermediate states in the plan, and we know exactly the cost of reaching the goal with this plan, right? Because we've got the cost of the actions. And so the training samples are going to be the hypergraph for the delete relaxation with the features corresponding to one of these intermediate states, and the cost to the goal, optimal cost to the goal from that state. We frame the problem of learning the weights as a regression problem where we optimize the mean square error loss between the perfect heuristic and the heuristic we produce. We average over a number of mini-batch problems from mini-batch, and we also average across the intermediate we obtain after different numbers of message passing rounds. So T here is the message passing round. And that's to do some gradual learning, not have to bridge the gap across 5 or 10 message passing round. The heuristic, even though we learn from the optimal heuristic, the heuristic that we get do not need to be admissible. There's no guarantee that they are, and how to generate admissible or likely admissible heuristic is an open problem. Right, so again, I want you to notice that in the experiment I'm going to show you, we do not use a lot of resources. We have 1 core, 2 gigabytes of memory. This is really small budget here. We train the networks using optimal plans produced by fast downward using the A* with the LM-cut heuristic. We do 5 rounds of message passing. We also experimented with 10, didn't really very significantly improve the results. And when we evaluate our heuristics, we solve the problem using A* for 5 minutes for each problem. We basically compare A* guided by our heuristic strips AGN to A* guided by LM-cut, which returns optimal plan, and A* guided by FF, which is a very high performance heuristic. So I'm going to show you a number of examples here. So we're going to learn over a number of problems from various domains. The first type of experiments is the single domain experiments, where we're going to learn from problems from a single domain. Let's say gripper here, for instance, which is a very small problem. And then we're going to evaluate on larger problems from this domain. So we're remaining within the same domain. And I will do the same for blocks world, for instance. And then the second type of experiments is multi-domain experiments. We're going to learn from domains problems from multiple domains, like gripper, blocks world, Zeno, for instance. And then we're going to evaluate using problems from one domain. It could be a domain that we learn from, or it could be a completely new domain, like Ferry or Sokoban. And so this is in line with our idea that, because at the end of the day, we're learning from graphs, we don't really mind whether the graph is a gripper or a Zeno problem, that we should be able at least to generalize sometimes to other domains. So let's start with blocks world. So in this first experiment, we are evaluating on blocks world, and we trained on blocks world. So you can see 3 graphs. For all of them, the x-axis represents the various evaluation problems, roughly ordered by order of difficulty. And then I plot the number of nodes expanded by A*, the runtime of A* with the various heuristics, and then also the deviation between the cost of the plan obtained and the optimal plan. All right, so in blue here, you have ASNet. In green, you have the optimal A* plus LM-cut, and in orange, you have A* plus FF. So you can see that we expand much fewer nodes than the other heuristics, which is good. On the other hand, this does not translate into gains in runtime, except maybe for the largest problems, for which starting to be competitive in terms of runtime. Because we don't expand a lot of nodes and we use A*, unfortunately, the cost deviation from the optimal is worse than, say, that of FF, even though FF is not an admissible heuristic for blocks world. So this is when we train on blocks world. Like when we train on multiple problems from multiple domains, including blocks world, we expand more nodes. So we're now very similar to the other heuristics. We're worse even in terms of runtime. We can't solve some of the problems. But on the other hand, because we expand more nodes, we get the optimal plan, which we weren't getting before. I'll give you another example. So Ferry, this benchmark, actually, I wanted to refresh my memory about what it does. I can't remember. It's embarrassing. So on Ferry, we expand much fewer nodes than the other heuristics, and we also do much better in terms of runtime. We solve more problems here that they can't solve, and we don't have a lot of cost deviation. So it seems we can really learn Ferry. And in fact, even if we don't train on Ferry, just learning from Gripper, Bloxworld, and Zeno, we get pretty good results. So I think it's because Ferry has a structure that is similar to this kind of problems, or some aspects of these problems. So that's kind of good here. And now to finish a hard problem, Sokoban. So Sokoban has got quite a different structure from all of these problems. It's much harder, as I said. You can see that we are competitive in terms of number of expanded nodes, the runtime, not so much. And we compute good plans with respect to FF, which is good because Sokoban can have very long plans. In fact, it's a p-space problem. You can have even exponentially long plans. So we're learning how to optimize plan costs. On the other hand, Sokoban being so different from those problems, we have very bad results if we don't learn a Sokoban and learn on those. So my takeaway on StripsAGN is that as far as we're aware, it's the first work that has tried to learn heuristics that have a chance to generalize to different domains, to domain-dependent heuristics. We do this by exploiting the hypergraph structure of the delete relaxation and learning over these hypergraphs. We can learn, I think I've convinced you, with very small amounts of data. One thing that I like is that this leads to new types of heuristics. I mean, when you have a look at these results on Ferry, I mean, obviously we get very different patterns, very different properties. We are unable to guarantee admissibility. That's a research problem. And the runtime is not competitive at present with the with dedicated planning heuristics implementation. And that's because the forward pass or through the hypergraph network is very time consuming. So there are a number of things we could do to improve that. We could learn from different types of graphs. We could use GPUs. We could also observe that one of the bottlenecks in our approach, both in AISNet and StripsAGN, is that the network we build are big because you ground, you generate all the propositions and actions. If we were able to exploit the relational structure of the problem in terms of predicates, action schemas, and objects, we get potentially much smaller networks that would scale better. So these are avenues for future work. Now to finish, I want to talk a bit about future work and how this fits with my goal of building planning system that combine learning and planning and are more trustworthy. So what do I mean by trustworthy? I mean that planning system must be effective, capable of handling real world problems, so sufficiently expressive and scalable. It must be safe in the sense of both robust and able to generalize to enforcing situation, but also in the sense of complying with constraints and verifiable. It must be explainable and also ethical. And I can easily argue, I think, that neither learning and planning, neither learning nor reasoning provides these properties. So for all of these properties, so for instance, reasoning is going to be very good to comply with constraints, maybe provide some guarees and being explainable, but it's not going to be very good at generalizing to unmodeled situations, and it's going to have difficulty to scale for expressive formalism. Whereas if we take learning, let's say reinforcement learning, for instance, the amount of data is going to be astronomical. It won't comply with constraint, won't be verifiable, it will be completely opaque. but it may be more robust and generalized better. So there is a need to combine these things. And so I'm going to talk about a little bit about each of the top three here with respect to the sort of approaches. So basically talk about the opportunities and challenges with respect to some of the type of approaches that I've talked about. So firstly, in terms of explainability, if you want to explain policies and plans, this creates some very interesting challenges. Most of the work that we see at the moment on explainability consists target classifiers that are used in a static setting, like classifiers for image processing and so on. If you want to explain policies, you're going to have to start reasoning about arbitrary long chains of repeated applications of these classifiers and on the successive world states that results in the global behavior. So I think there's a lot of opportunity here to extend the work that's been done at NIT by Nicolas or Joao on explaining more ordinary classifiers to planning. Another problem that I find is interesting is how can we provide interpretable descriptions, good descriptions of what a generalized policy does. So we've experimented, for instance, with AISNets, generating sparse AISNets. That's one for triangle tile world, and converting them into a set of equations such that someone like me inspecting those equations would convince myself that what this policy does is going through the edge of the triangle. But really, I think we're very far away from automatically generating a sentence saying exactly that this policy tells you to go around the edge until you reach the goal. I think it's a fascinating problem. Another important issue is to be able to justify why a plan was chosen over another. And in order to do that, you have to compare the properties of a plan with potentially all of the other possible plans. You have to start looking at the space of possible plans and looking at why was this plan presenting a better trade-off than plans having other properties. So there's very interesting work being done right now by Jörg Hoffmann and his students on this. In terms of safety, I'm going to say just that for verification, my view, my impression, not working on this, is that the challenges are very similar to explainability. You have to reason about this chain of repeated applications of policy classifiers. And for this, you're going to have to build symbolic abstractions of neural networks so we can reuse the machinery of model checking, deduction, and all that. In terms of safety, as in handling constraints, we're starting to see very interesting work combining Lagrangian relaxation and other techniques to handle constraints as part of the optimization problem solved by deep learning. If you talk to deep learning people, they will tell you that for them, the holy grail is having differentiable reasoning. And whilst I think it's a good avenue of research, I would like to see also complementary avenues of research where we depart a little bit from the old differentiable and the gradient descent to learn, and instead try to build much more effective parallel combinatorial optimization solver, the future MaxSat solvers, which we can also use to solve learning problems and which will be able to handle much richer class of constraints. Now, one way of guaranteeing safety is to use search, and then you only use deep learning to guide search. So I've shown you an example with StripSIGN where we're using A* guided by a learned heuristic. But there are many other options. For instance, we experimented with guiding Monte Carlo tree search with AISNet policies by essentially transforming the node selection mechanism of Monte Carlo tree search to bias it towards the actions that AISNets say should be applicable with high probability in the policy. And interestingly, even if Monte Carlo tree search on its own or AISNet on its own is incapable of solving some problems, once you combine them, it can solve a lot more problems. That's because part of the ASNet policy are actually useful in guiding Monte Carlo research, even though the policy as a whole is not useful. So this is my last slide. I just want to talk a little bit about what would need to happen to improve the effectiveness of the sort of approach that I've mentioned. So for me, what we need to do is to have a much tighter integration between learning and search than what I've shown you. So what I want is search algorithm that can not only look for solution, but also learn while they're doing that and generating their own examples whilst they're doing that. So for instance, if we were using generalized heuristics and policies, we could do that because these can learn from the example generated at any point in the search, because they are not tied to a particular initial state goal or number of objects. And they can help bootstrapping to solve larger problems, because you can start learning with so-so heuristic on small problems. As part of the search, you're going to improve it. It's going to enable you to solve bigger problems and learn from these bigger problems and so on. Okay, I'm going to skip that just to finish the last, well, another area in which deep learning could be, or learning could be useful, is really helping to learn domain models. So planning models are notoriously time-consuming to build. And so being able to learn them from a range of modalities like traces of states, text and video would be really useful. And whilst there's been in the past, in fact, since the 80s, work that tries to do that from traces, I think we should really start using the latest advance in machine learning, to be able to do this better. And so there are many interesting problems and many challenges and opportunities. And so if you're interested in working on this, together, drop me an email. All right, thank you. Thank you for listening, and sorry for going over time for a change.
Thank you so much, Sylvie, for very, very rich talk, very, very exciting, very nice. So the floor is open for questions. I should have said that you could, of course, use the chat to put your questions in as you thought of them, but nobody did. So the floor is open for anybody to pick up. I forgot to tell you about the chat. Yeah, I'm sorry. Well, I guess I'll start. Sylvie, so there's something that I wanted to ask you about. I really don't know the answer to this. It's really something more that Luc Dorette was talking about when, and this is more about the ASNet than the graphical model.
Mm-hmm.
So just a little bit of background. So people have been trying to put logic into deep learning, and they've sometimes tried to reflect the logic in the architecture of the net, right? So to put modus ponens, you might have an action, a transition arrow that takes you from PROQ and P to a new state Q, right? And so, and then you could put weights on it and use that for reasoning. And Dorette says, well, this is a problem with this is that as you learn, the weights may actually not continue to validate logically valid laws. So in some sense, as you learn, you might forget your logic. And I'm wondering whether, is this at all a danger in the ASNet planning architecture that you start out with, the logic of the plan, but as you learn stuff and maybe weights get lower, then things that are really logically valid inferences, at least in something like okay,
so well, I would love to I think I can kind of see how this can happen with logic. So what do I want to say here? So one thing is that in ASNets, we're really only using the network, I would say, to propagate information as opposed to doing really deep reasoning and inference. So I'm guessing, even though I don't know Problog very well, I'd have to have a look. But I'm guessing that yeah, there is a bit more semantics going on in these problem networks than we have in ISNet. So that would be my first reaction. And I would also add that because we're so what could happen that would be bad is either we don't reach the goal, or we're not going to apply actions that are not applicable, because you remember we're actually ruling them out. So this kind of thing's not going to happen. And I think I can convince myself that if we had arbitrarily long network, we wouldn't have the problem of receptive field. And I also think we could potentially learn to solve any problem if we didn't have this limitation. So I don't know that, I have to look. This is a very good question. Thanks for asking. I need to have a look and understand the problem and see whether this can happen. Thanks. Yeah. Sorry, I can't answer it better.
No, thank you. It's an open question. I don't know the answer either. I've seen Doré does give a kind of convincing argument about that. But for inference, and the inferences are, it could be more complicated, and the weights might play a larger role there in the propagation of information than they do in your
setup. And you have to see also inference. If you say something is true, I mean, it's got to be true, right? I mean, like here, we're applying action as long as the probabilities are not too bad. We're not trying to generate optimal plans. So I think we're on safer grounds. That's something that actually tried to do some logical reasoning and needs to get its answers perfectly right.
Yeah, thank you. Okay. Other people, please chime in.
Hi, Sylvie. It was a very nice talk, and I'd just like to ask a quick question about the no admissibility guarantee, which I wondered if you have any ideas of perhaps integrating some guarantee of admissibility for the heuristics.
So I mean, I haven't been following that work carefully, but there's some work that started to, I mean, actually the concept is older than deep learning, things like this, but it's the concept of likely admissible heuristics. So so this is one of the things that could be used. I mean, it's a probabilistic guarantee. It's not going to be a sharp guarantee. I am not, to be honest, this is one of these things on my list of to-dos, but I have not had time to really thought about how one could do something better than providing some sort of probabilistic guarantees. But there is this concept, likely admissible heuristics. I think it's, is it Marco Gori? Actually a while back, and this is becoming popular again with the advance of deep learning.
Okay, thank you.
We have a question from Mohammed Kanish, which is for you, Sylvie, which is, can you report on the industrial applications that you have addressed with these approaches?
Okay, so I mean, I have not addressed any industrial application with these approaches. I do work on applications, but not on, at the moment, using different approaches. So I'm assuming you mean this deep learning approach as opposed to, planning. But I'm kind of interested to see whether we can apply this to some of the kind of problems in manufacturing where, a robot maybe would have just a small number of tasks that it can do, but maybe using a range of tools, and basically use the generalization capabilities of ISNets to generalize to different settings. So maybe learning in one setting with certain type of tools and see whether this can generalize to other sets. Another thing really interesting, I think, is in the cooking domain. So Sony has got this Gastronomy Ai kind of big project. I don't know whether you've heard of it, where robots and AI assist chefs in cooking at all sorts of levels. And I was thinking that it could be a good application to try to basically learn how to, combine ingredients and cook recipes. I don't know. I mean, so this is one of the things that I would like to do. And this is really early days, right? I mean, I've said at the beginning, 2 honors, 2 undergraduate students, so we're just starting. But I know that many companies are interested in using both deep learning and planning. They find out that deep learning on its own doesn't really work for this kind of planning or scheduling problems, and so they're interested in combining both.
Other question, Luis. So Luis says, in the policy and heuristic learning problems that you presented, do you save anything on the modeling side?
Okay. So yeah. So I interpret the question as, well, you still need a model, right?
Yeah.
Yeah. So I do still need a model, and this is why at the moment we're not on par with reinforcement learning. And this is why I would like to be able to learn the models, because then will be exactly that, like what Yann Lequin says, learn the models, and then you can use these models to, for this kind of approaches. I mean, it would be interesting to see whether we can learn less reliable models and still obtain, less reliable models than what you would need for planning. Because we're going to actually learn from plans, from example of plans. But at the moment, yeah, I have not investigated that question. That's a good question.
Thank you.
Yeah, along that line, so can you say a little bit more about learning these sort of inaccurate models? I think that's very interesting, because I'm just thinking about that with respect to explanations. And so we have these models, so we have explanations and counterfactual models built on causal graphs by Pearl and company. And one thing that, the students Luca de Lara and Alberto Gonzalez Sainz have shown is, okay, maybe we can learn something approximating that model more efficiently than finding the true causal graph from data, which is an NP-hard problem, and probably finding the true plan structure, the true model that you want to look at is also NP-hard at least in your setting.
Okay, so I mean, I'm going to start by answering maybe a slightly different question, just because you seem to be interested in knowing what's been done. So what's been done so far in learning models is, for instance, people have observed a whole bunch of traces of states. They don't need to be complete, and so they form some sort of optimization problem, say, that ties up the possible preconditions and effects with what they observed in these states. So that's what's been done so far. There's also been some work learning hierarchical models of hierarchical test networks. In fact, Malik has been working on this. So my intuition is that, for ISNet, we really don't need, we really need preconditions and effects, and we don't necessarily need, by doing that, to, let me see. So again, I guess I don't have the answer, but my sense is that you could get some good results, and you could combine learning the model with learning how to use it when, like for instance, in an ISNet. It's kind of interesting that if you ever look at the work that's being done in reinforcement learning at the moment, even when they have a model or knowledge, they throw it completely away, and they get the network to learn just enough of what they need to be able to decide actions. So it should be able to, we could be able to do something like this, but I'd like it to be more, more structured, that there is really a model learning part, and then there is a planning, a planned learning part, whereas reinforcement learning tends to mix up those things in a way that results in having, lots of data being used.
Okay, thank you. Oh, more on the planning side from Alexandre Albor. You've shown that you perform quite well on the ferry problem. A boat has to ferry a car from one location to another. The domain has few actions: sail, board, debark. So how much of the apparent simplicity of the domain effects and the size of the hypergraph do you build and eventually the performance? Bon, Alexandre, j'ai pas tout à fait compris la dernière partie de ta question, donc tu peux...
Salut.
Excuse-moi.
Salut. So the ferry problem is quite simple. You have to move a car from position to another. And you have very few actions. You have to board the car on the ferry, to sail the ferry, and then to debark the car. So I was wondering how much the apparent simplicity of the problem, the planning problem, affects the representation you build of it, and then eventually the performances you have, because
so I'm guessing there's a number of things here. You're right. Okay, so I wanted to look up ferry. I was thinking, remember to look up ferry at least. So thanks for reminding me what it is. So I'm not surprised, therefore, that we've got good results on such a simple problem. And I'm also not surprised that the runtime is pretty good, because then you will have, you won't have this whole bottleneck of the forward pass on huge graphs. But I should say that what I find interesting is that you can still learn Ferry because it's got very simple operations that are probably, which you can get from Gripper and Bloxworld. So you can still learn Ferry from bigger graphs, which we've done here by doing, Bloxworld, that's much bigger. And we can still extract the essence of it. So it seems that we can learn on bigger graphs, right? I mean, that this is what the second picture shows, and still basically get the same results, which are probably warranted by the simplicity. Do you see what I mean? I mean, so there is a part of me that's saying, yeah, it works well because Ferry is simple, but on the other hand, we get that simple structure. We manage to capture it by learning on these bigger graphs for Gripper, Bloxworld, which don't have Ferry, because the operations are probably a small subset of what you would get. I mean, the Ferry operations are probably a small subset of what you would get in Gripper, Bloxworld.
Yeah, that's right. They're kind of similar in some way.
Yeah, and Gripper, we get good results, of course, as well. If you're interested, you will find more results in the paper, and I think on a talk I gave a little while ago. But yeah, okay. So we really need to do a lot of work in analyzing those results and their significance. And I think we haven't done this to the extent possible in the conference paper, and hoping to do it in a journal paper when we have time.
Cool, thank you.
Okay, great. Any other questions? D'autres questions?
If there are not other questions, I have another one. Sorry to monopolize.
No, go ahead, Alexandre.
Okay, so about the quality of the plants, because we're saying that we're suboptimal, we're comparing to FF, which is suboptimal as well. But there are some works of Giuseppe Di Giacomo about triggering the reward function. Okay? He represents it with the finite state machine.
Yeah.
So to push the learning in a desired direction.
So is that this restraining bolts?
Yes, exactly, the restraining bolts.
Okay. Yeah.
With analogy to Star Wars.
Yeah.
So the idea is to put preferences, but seen from the learning point of view, on the preferred, yes, on the preferred plants we want. Have you thought about that? How do you see this can impact the quality of plants in such a context?
So yeah, I should have looked at the restraining bolts again. I can't remember. So you say they are basically preferences on plants, or
what it is, it uses a finite state machine that depends on the state of the
to
planner.
represent the plants?
Yes, exactly. And this state machine provides a different reward function depending on the state.
Yeah. Okay. Right. Okay. Yeah. So it's some sort of reward, clever reward shaping. You'd say,
Exactly.
right?
Yes.
Okay.
It's
So
not done by LTL, but with a finite state machine.
yeah.
Almost the same.
So in things like strips AGN or even ASNets, we haven't used rewards, right? So at the moment we're using just plants, but I think especially strips AGN, it's very modular. You know, we could learn all sorts of stuff. We could learn, I don't know, suboptimal plans. We could learn with rewards. So I think it should be possible to, yeah, actually it's a good idea. I think it should be possible to try to replicate this in a kind of slightly different setting. I mean, learning setting where we would have rewards and so more information actually, because we only get, you know, the plants. And yeah, and get some good results. So that's a good idea. Maybe we should work on it together. Yeah. So I think, yeah, we should. I'm really keen on exploring other usage for these architectures like strips AGN or graph networks, which have got, yeah, in different settings like rewards or something like this.
Okay. Well, great. Thank you. I guess, Sylvie, thank you so much for this talk. It's given us a lot to think about, a lot to work on, and, you know, a lot of exciting trends here. And, you know, I'm sure we'll come bother you later.
Well,
and thanks again. I
yeah.
guess we'll close now. Okay.
Yeah, and thanks again for inviting me. It was a pleasure to, yeah, catch up with you guys.
Okay. À bientôt.
Oui,
Merci.
à très bientôt. Au
À
revoir
très
tout le monde.
bientôt tout le monde. Salut.
Au revoir.
Merci. Au revoir.
Au revoir.
Au revoir, merci.
Bye.